Okay, this is about question 2 from midterm exam. In the midterm exam questions, we have these equations, the standard equation, and this is how M is measured, midterm is measured, how final is measured. Okay, and assumptions are first, obviously, the error terms. I forgot to mention this, by the way. I had to say that the error terms should be 0. Let me see if this is required, why this is required. And anyhow, these are the 3 equations we are going to number formula 1, 2, 3. And the first equation, first thing, estimating equation is to regress y on m. By the way, so when you analyze this kind of model, first thing I suggest is to think about what is the primitive, what is exogenous, what is underlying, fundamental variables. In here, in this model, y, m, f are generated from x, u, w, epsilon. Okay, so left-hand side variables are endogenous variables, right? They are results of these equations. So when you handle these assumptions, when you handle the model, usually you need to think about those bases, like underlying variables first. That is, like, for example, when you have the equation 1 and equation 2, then from equation 1 and equations 1 and 2, we have so you want to connect x with like m, replace x with m, and then you can do it by adding and subtracting, right? And then you can rewrite this as plus here, plus where tilde epsilon is this guy. Okay, so I try to maintain the basic structure that left-hand side is y and right-hand side is exogenous variables, like underlying variables. Okay. And by the way, I'm going to give you a tip here, leaks tip here. When you write equations, you'd like to number the equations and cite those, refer to those equations later. But it's really annoying if, for example, like later when you edit the thing, for example, I want to write a new equation like say 1 plus 1 equals 2. And if you number this line, then this becomes number 2. So you have to manually change equation numbers like this, right? But a better way, of course, this is not how you do it. I recommend you use equation label, right? Equation label is, say, I will call this salary equation. And I'm going to label the second equation as, so this is equation midterm equation. So I put names, labels on these equations, and then what I cite here is this number 2 means salary equation. So then I will include, put insert and cross-reference. Use cross-reference here, and I will mention salary equation. And then later, when you compile this into a PDF file, automatically this number will be used in this place. And here, number 3 will be a midterm equation. Okay, let's see what happened if you compile by pressing here, Control R. So you have number 2 and number 3 correctly from these two types. Okay, and so let's see what happens if you erase the equation. I will erase, close that. Oh, no. And let's try what happened when you do not have, like now numbers change it, like from 1 and 2, from 2 and 3, now it is 1 and 2. Error. Why? Okay. So now it is correctly number 1 and 2. 1 and 2. So this is really, really useful. Like when you write a dissertation, like you can have like, I don't know, maybe in my dissertation I had more than 50 equations, and all of them are cited somewhere in the paper. So then managing those numbers is really hard. But so there is technology, right? Okay, this is really useful technique. And by the way, what I wanted to say, here, so you may write it this way, and then you can show covariance between M and the new error term is not 0. So in the estimating equation, beta is correct, but you cannot estimate this correctly because exogeneity is a problem. Or you may start directly from regression of y on m. That is, we want to study the bias by this. So when you regress y on m, you are going to estimate this as the coefficients. We hope this equals beta 0, but there it's different. The difference is the bias, right? So then let's calculate this difference, that is the bias. To calculate that, like let's calculate that each terms. Covariance between y and m can be written as, like, you are going to use this equation again, right? You use this equation again because of this endogenate, like use that equation to replace y something like this. Then, like, you know the details of the algebra, right? Like this, okay? And then now you can say that this is not 0. You can show that, but covariance is covariance this guy and between this guy and this guy. And as you see, u are repeated, so it is minus beta 0 variance of u I. Because x is uncorrelated with like epsilon and u. Also, epsilon and u are uncorrelated. Okay, so And furthermore, like, so as a result, so the bias is like this divided by this, or like, let's put it this way, say, so divided by this minus beta 0, and as you know, a term cancels out, and this only have covariance divided by variance, right? And as I said, it would be more natural. Put it here. And like here, this is not the end. I don't recommend you to finish here because, as I mentioned earlier, m is endogenous variable and epsilon tilde is just temporary variable. Like it does not exist. It's not a real substantial variable. I just like think about a new variable because we have to think about an estimating equation, right? So, and then the variance of m is like variance of xi plus ui. So that is like variance of x plus variance of u. They are uncorrelated. That is, in the end, the bias, the best answer is like this, minus beta 0 variance x divided by this guy, right? That is the bias, okay? This is how you do it. Or just you can directly you can plug in equation 1 into here, plug equation 2 directly into there, and in the end you will get the same thing. And the main point here is do not leave endogenous variable in your answer when you think about it. So it's 99%, like it's not 100% rule, but general tip, like that will help you solve out the algebra easily. Okay. And then once you do it, then the following questions will be easier, right? Here, like check the instrument. You can check like relevance condition means covariance between M and F is not 0. It is easy, so I will skip that. Exogeneity or validity of the instrument is this, right? So this is easier. It's also easy to show because epsilon tilde is given here like this, and F is uncorrelated with all of them. I had to mention that. So covariance xi epsilon is 0, covariance xi ui is 0, covariance xi wi is 0, and covariance x like ui wi is 0, and covariance ui epsilon I is 0 equals 0. Everything is 0. And you have to assume that everything is uncorrelated. All the underlying variables are pairwise uncorrelated, right? So you can think about all the pairs and they are all uncorrelated. So then you can show this easily. Okay. Then the moment condition approach or the fitted value approach, you may use either. Let's think about identification based on the moment condition approach. So if you want, you may use all these conditions at the same time. That is possible, but you don't need all of them. And we know that this is enough. And these two are enough to identify two parameters. Because anyhow, we would like to identify alpha and beta, and so then you need two moment conditions for two identification of two parameters. Then usually we use like exogeneity of the instrument and location normalization. Mean is intercept, mean is 0. So without this, still you will be able to identify beta, but alpha is not identified. But formality, I'm going to include that. From here, then, I believe it should be simple enough. You can rewrite, you can set up a system of two linear equations for two parameters. So pretty simple, simple argument. So I will skip the details. I think, and requirement is full rank assumption. That is also provided like by these assumptions by these equations. Already M and F are correlated, and if those variables are not constant, like if those eta terms and x and all the things have non-zero variance, that's enough. That's enough for the full rank assumption. Okay, let me do it. From the first equation, okay, so I will think about this yi minus alpha 0 minus beta 0 mi is epsilon tilde, and fi times yi minus alpha 0 beta 0 mi, right, equals 0. Its expectations are 0. Right? By the way, I had to mention this. Covariance of f tilde variance 0. Combine this equals minus expectation f times expectation tilde variance tilde variable epsilon. And then, but by the second equation, second assumption, this is 0. So tilde. So you can simplify the covariance into expectation because we assumed scale like location normalization. Because of this normalization, you can replace covariance with expectation, right? And we can start the moment function approach. Otherwise, you have to maintain covariance from here. If you do not have this, that means you are going to use only one, a moment function, a moment condition. That is okay, but you have to keep the covariance form, right? But because I make two assumptions, you may replace covariance with expectation. And from there, you write this as expectation y and expectation fi minus, it will be 2 by 2 matrix of, let's see, 1 expectation m, and here you have um, expectation f and expectation fi and I multiply parameters. Okay, so by rearranging the terms, the equation, we get this equals this. If the matrix on the right hand side is invariable, or the parameters are identified. For the matrix to be invariable, we need the determinant. Determinant is this, right? Its determinant to be non-zero, which is equivalent to following condition. Okay, something like this. And you can show that covariance is not zero. It is pretty simple. So I believe you can do that, right? This is pretty simple, even though I ask you to be rigorous, but actually nothing special at all. Okay. Now let's think about the fitted value approach. If you use the fitted value approach, let's think about the second stage. Second stage, the equation is the same, not the same, this one. Second stage equation was this, but the main problem was M was endogenous. M is endogenous, correlated with epsilon tilde. And then, like, I will think about the first stage equation, which is a regression of M, endogenous variable, on the instrument F. And we assume variance between F and is 0, right? And then how can we identify that? Like, then this and variance between F and then plug the second equation into the first one. Then you will get so what is interesting is our original error term was epsilon, but because x is not observed, we have to replace x with m, and then we have another error term that includes the measurement error in the error in the score, and then because the test score is endogenous, we replace this with its fitted value from the first stage regression. So as a result, we have another error term, right? So how do we write this? Like, I don't have a good idea, just whatever. I will simply call that as E, right? Now, if you can show, and I will define a new notation, head mi. So where E is defined as like this, and head M is defined as this guy, right? And then what you have to show here is you have to show that hat M is satisfies the exogeneity and the full rank conditions. Then you identify beta 0. So this identification relies on two things. First, this derivation. This is the first derivation you have to show, and then define the first stage equation and use the two-stage equation thing. Okay, so this part is to handle unobserved x, and then to handle endogeneity, you need to set up this much. This is what I expected, and somehow expected, but somehow surprisingly, many of you have incomplete arguments. Like your arguments are not perfect, but I hope this helps. Okay, anyhow, you did well. Sorry for the delay, and I will see you in class. Bye.